So I'm sitting here looking at these flowers, and we're going to refer to them to talk a little bit about color and how we perceive color. So we have here these red geraniums. Start off with these, and we can use them as an example of what color really is. So I have the window open. There's light coming in from outside. The light contains a variety of wavelengths, short, medium, and long wavelengths of light. And remember, the visible spectrum is between 400 to 700 nanometers in wavelength. So that light's coming in. It's hitting the surface of the petals. The petals are absorbing most of that light, actually, but reflecting the longer wavelengths. The longer wavelengths then reflect off of the flower. They're the ones that go into my eye and allow me to perceive that as red. Now for the color green, we see here on the stem, it's a very similar process. It's just a different range of wavelengths that the green stem is reflecting. So once again, the sunlight is producing short, medium, and long wavelengths. They're coming into the window. In this case, the stem is absorbing the short wavelengths and the long wavelengths, but reflecting the medium ones. And so those medium wavelengths reflect off, enter my eye, and then I end up perceiving those as green. Some colors, like this orangish yellow of the poppy, are a combination of more than one wavelength. And white is a combination of all wavelengths, short, medium, and long, in approximately equal quantities. And black would be very little light reflecting off of an object at equal levels. So just almost all of the light is being absorbed by this black pen. So normal color vision relies on our visual system having the ability to detect and distinguish between these three different wavelengths, the short, medium, and long wavelengths. And this was determined actually a long time ago, before researchers had the ability to look in the retina and find these receptors for short, medium, and long wavelengths of light. And so trichromatic theory, also known as Young-Helmholtz theory, was figured out just using observations of humans and their perceptions of color. And what they determined was that if an individual could control, say, 3 lamps, a red one, a green one, and a blue one, if they combined those 3 light colors of light together equally, they got white. And if you took white light and you used a prism to separate out the different wavelengths of light, then you could see the individual colors, just like what happens in a rainbow, right? And so they were able to deduce that there's something really important about these 3 colors, red, green, blue. And out of these three colors, red, green, blue, you could create any other color in the rainbow, actually, through different combinations of a little bit of short, a lot of medium, and a lot of red, for example, would produce one color, and a little bit of short, a lot of medium, but just a little bit of long would produce a different color. So they figured out that all you need are these 3 different colors of light, and you could create any color in the rainbow. And so they figured out early on, again, that normal color vision relies on having these 3 types of cones. So colors, remember, are determined by the wavelength of light, but wavelength is not color. Our color is a perception. It's an experience that we have. It's a conscious experience. It is a code created by our nervous system. Our brains interpret that wavelength. There is nothing red about long wavelengths of light. There's nothing blue about short wavelengths of light, and there's really nothing green about medium wavelengths of light. It's all a perception. Now, this picture I think is really interesting. It has these little dots. These little dots are each a different type of cone in our retina. And the ones shown in red are the red cones that that detect long wavelength light. The ones shown in green are the ones that help us see the color green, perceive the color green, and they detect medium wavelength light. And the blue ones are the ones that help us detect the short wavelengths of light that we perceive as blue. And you can see that there's not an equal number of each, huh? There's a lot more of the red ones, the long wavelength cones, than there are of the short wavelength cones. And that tells us then that in general our color vision is a little better for reds and greens than it is for blues. When the cones receive all wavelengths of light in equal amounts, short, medium, and long, we perceive white. And the way we do that, we see that all the time, is if you ever go to a live production, a live theater, or some other, like a stage production, concert, those types of places, they'll have these stage lights. And if you combine a red, a green, and a blue stage light, in the middle you'll get white. And you'll perceive white because that area is going to have an equal amount of short, medium, and long wavelengths. Now, different thing happens when we start playing around with paints. And we all did this probably as kids, right? So you mix paint colors and eventually you get like a very dark brown or a black. The reason for that is that paint changes the surface of an object. So if you start off with a white piece of paper, that white piece of paper is originally reflecting all the wavelengths of light equally. So if you have white light, like sunlight, you're going to see a white sheet of paper. If you now take a red marker or a red paintbrush and you paint that piece of paper with red, what is happening is you're changing the wavelength that that piece of paper is going to start absorbing. That piece of paper now is going to be absorbing short wavelengths and medium wavelengths and only reflecting the long ones. The long ones reflect off that piece of paper, go into our eyes, and we see red. If you do that with more and more colors, eventually you have a surface that is absorbing short wavelengths, medium wavelengths, and long wavelengths. And so you see black. So together, the different paints will capture all the wavelengths. And then none of them are going to be reflected by that part of the paper, and it'll appear black.